Today we are going to do chemistry of noble gases from modern approach to inorganic chemistry by Dr. S.P. Jauhar. So the elements helium, neon, argon, krypton, xenon, and radon comprise noble gases. The group of noble gases is regarded as zero group or group 18 of the periodic table. These are gases at ordinary temperature and do not have chemical reactivity. Due to chemical inertness, these were called inert gases. However, nowadays, a number of compounds of these gases, particularly of xenon and krypton, have been prepared. This shows that these gases are not completely inert. Consequently, these gases are called noble gases instead of inert gases, which signifies that these gases have some reactivity. Because of the low abundance of these gases on Earth, they have also been called rare gases. Occurrence of noble gases. The noble gases occur only as minor constituents in the atmosphere. Due to the inert nature of these gases, they always occur in the free state. Except radon, all these gases are present in atmosphere in the atomic state. The amount of noble gases present in the atmosphere. Helium is also present in natural gas to the extent of 2 to 7%. It is also present in small quantities in minerals of radioactive elements such as monazite, clavite, pitchblende, etc. Helium, neon, and argon are found in the water of certain springs. Radon is radioactive and does not occur in the free state because it decays very rapidly. Helium was first discovered in Sun's atmosphere. It is now known that helium is being constantly produced in Sun's atmosphere by nuclear fusion reaction involving the formation of helium nucleus from 4 hydrogen atoms. History of discovery of noble gases. Noble gases are mostly present in the atmosphere. Their discovery is briefly discussed as follows. Discovery of argon. The main credit for the discovery of first noble gas, argon, goes to Cavendish. In 1785, Henry Cavendish performed a number of experiments to determine the composition of air. He passed repeated electric sparks in a dry sample of air with an excess of oxygen to convert nitrogen of the air into nitrogen dioxide. According to the reaction, nitrogen plus oxygen gives nitrogen dioxide. The gaseous mixture containing nitrogen dioxide and unreacted oxygen was absorbed in alkaline potassium sulfide solution. He observed that a small amount of residual gas, about 1 by 20th of the original volume of air, was always left behind. He repeated the experiment again and again, and every time observed small traces of residual gas which was neither oxygen nor nitrogen. He could not understand the nature of this residual gas, which could not combine with nitrogen. He could not understand the nature of the residual gas, which could not combine with oxygen. However, the observation of Cavendish remained unnoticed for over a century. In 1894, Lord Rayleigh observed that the density of nitrogen isolated from the atmosphere is about 0.47%, higher than the density of nitrogen prepared in the laboratory by the thermal decomposition of ammonium nitrate. Ammonium nitrate gives nitrogen plus water. This minor discrepancy would have been ignored by many investigators. Then Rayleigh, in collaboration with Ramsay, repeated the earlier experiments of Cavendish and concluded that the residual gas contained a new gas different from nitrogen. It was examined carefully by spectroscopy and was found to be an unknown gas. The new gas was named argon. Greek argos meaning inert or idle. Second is the discovery of helium. Helium was first detected spectroscopically by Lockyer in Sun's atmosphere in the year 1868 while examining chromosphere of the Sun during total eclipse. As a result of their investigations, they concluded a new element called helium, Greek helios meaning sun. Later on, Ramsay in 1895 also detected the gas on Earth from the radioactive mineral clavite. Kessler in the same year detected helium in traces in the atmosphere. Third is the discovery of neon, krypton, and xenon. Ramsay and Travers performed certain experiments on argon, suspecting it to be a mixture of a number of similar constituent gases. They repeated experiments on liquefaction of air and its fractional distillation. The first fraction was found to contain new element which gave a different spectrum. The element was called neon. Greek neos meaning new. Shortly afterwards, they discovered two more new elements on further fractional distillation called krypton, meaning hidden, and xenon, meaning stranger. Next is the discovery of radon. Radon was discovered by Dawn in 1902 as a result of the study of the disintegration products of radium. Position of noble gases in periodic table. While building up the periodic table of elements, Mendeleev had not left any space for the noble gases. Obviously, he could not imagine the existence of elements which have almost no chemical reactivity. Ramsay, the main discoverer of these gases, proposed a new group for these elements on the basis of their atomic masses and lack of their chemical reactivity. This group is called zero group of the periodic table. The zero group also suggests chemical inertness or zero valency. Before the discovery of noble gases, there was a sudden change from the electronegative halogens on right hand side to most electropositive alkali metals on left hand side in the periodic table. The addition of zero group between seventh A group and first A group has solved this anomaly. The position of noble gases in the periodic table was later on confirmed by Moseley, who constructed the periodic table on the basis of atomic numbers. The values of atomic number of noble gases strongly suggest that they should be placed after halogens and before alkali metals. General characteristics of noble gases. Electronic configuration. Except helium, the atoms of all noble gases have 8 electrons in the valence shell. The general electronic configuration of noble gases, except helium, may be expressed as ns2 np6. Helium has the electronic configuration 1s2. These configurations being stable, the noble gases neither have any tendency to gain nor lose electrons, and therefore they do not enter into chemical combinations. It is therefore reasonable to assume that the inert nature of noble gases is due to their stable electronic configurations. Physical properties. Some of the important physical constants of noble gases are given in Table 1 and these are discussed below. First is existence. All the noble gases are monoatomic, colorless, and odorless. The monoatomic state of these gases is due to stable electronic configuration of their atoms. As a result, they are not capable of combining even amongst themselves. The monoatomic nature of these gases is confirmed by their values of Cp by Cv, where Cp and Cv are the molar heat capacity at constant pressure and at constant volume, equal to 1.66. It is observed that for all monoatomic gases, Cp by Cv is close to 1.66. Second is atomic radii. In the case of noble gases, the atomic radii correspond to van der Waals radii. As we go down the group, the van der Waals radius increases due to the addition of new electronic cells. Ionization energies. The first ionization energies of noble gases are very high. This is attributed to the stable, completely filled configurations of noble gases. However, the ionization energies decreases with increase in atomic number from helium to radium due to increasing atomic size. Fourth is electron affinity. Due to the stable Ns2 and p6 electronic configurations, noble gas atoms have no tendency to accept additional electrons. Therefore, the electron affinities are nearly zero. Fifth is the melting and boiling point. The melting and boiling point of noble gases are very low in comparison to those of other substances of comparable atomic and molecular masses. This indicates that there are no strong attractive forces between the atoms which may hold the atoms together in the liquid or in the solid state. It has been established that only weak van der Waals forces are present between the atoms of the noble gases in the liquid or the solid state. These van der Waals forces increase with the increase in atomic size of the atom, and therefore the boiling points and melting points increases from helium to radon. Sixth is ease of liquefaction. The noble gases are not easily liquefied. This is due to the fact that there are only weak van der Waals forces which hold atoms together. This is also clear from low values of heat of vaporization of these gases. Due to increase in atomic size and therefore increase in van der Waals forces, the ease of liquefaction increases down the graph from helium to radon. Seventh is solubility in water. The noble gases are only slightly soluble in water. The solubility in general increases from helium to radon. The solubility of noble gases in water is due to dipole-induced dipole interactions. Water is a polar molecule. When it comes near a noble gas atom, it induces dipole in the noble gas atom by distorting or polarizing the symmetrical electron cloud of noble gas atom. As a result, an induced dipole appears on the noble gas atom, leading to interaction with the dipole of polar water molecule. Therefore, because of dipole-induced dipole interactions between water molecules and noble gas atoms, the noble gas dissolves in water. As the size of noble gas atom increases, the extent of polarization also increases. Consequently, the magnitude of the dipole-induced dipole interactions increases and hence the solubility of the noble gas in water increases from helium to radon. It is general chemical characteristics. In general, noble gases are not very reactive. Their inertness to chemical reactivity is attributed to the following reason. First is the noble gases have completely filled Ns2 and P6 electronic configurations in their valence shells. Second is the noble gases have very high ionization energies. Third is the electron affinities of noble gases are almost zero. Therefore, they have neither tendency to gain nor to lose any electron and do not enter into chemical combinations. However, in recent years, it has been found that noble gases, particularly xenon and krypton, form some compounds. Chemistry of compounds of noble gases. Prior to 1962, it was believed that noble gases do not combine at all, and no compounds of noble gases were formed. Though, from time to time, some attempts have been made to test the reactivity of noble gases, yet the gases were thought to be inert. This was also supported by the following reasons. The atoms have stable, completely filled electronic shells. They have high ionization energies. The noble gases have almost zero electron affinities. Therefore, they do not have any tendency to gain, lose, or share electrons with other atoms. The above reason discouraged the chemists to make serious attempts to prepare compounds of noble gases. In 1962, N. Bartlett, while investigating the chemistry of platinum fluoride, noticed that platinum hexafluoride acts as a powerful oxidizing agent which combines with molecular oxygen to form ionic compound dioxygenyl hexafluoroplatinate, that is oxygen plus platinum fluoride gives dioxygenyl hexafluoroplatinate. This indicates that platinum fluoride has oxidized O2 to O2 positive. Now, oxygen and xenon have some similarities, and this led Bartlett to try reaction between xenon and platinum fluoride in a similar manner. For example, the first ionization energies of xenon gas is comparable to that of oxygen. For the process, O2 gives O2 positive plus electron. Second is the molecular diameter of oxygen and atomic radius of xenon are almost same, that is 4 angstrom. With this assumption, Bartlett reacted xenon and platinum hexafluoride in gas phase and an orange-yellow solid xenon hexafluoroplatinate of the composition xenon platinum fluoride was obtained. On analysis, this compound was found to be an ionic compound, and this marked the first compound of any noble gas. The formation of this compound has demonstrated that xenon is not totally inert, and it is possible to remove an electron from xenon atom. This discovery attracted many scientists for active research for the preparation of other noble gas compounds. Within a few months, xenon fluoride and xenon fluoride have been prepared in the laboratories. Thus, noble gas chemistry began. Among these noble gases, xenon forms a large number of compounds with fluorine or with oxygen, and krypton forms only a few compounds. Some important stable compounds of xenon in different oxidation states are listed in Table 3. Before discussing the chemistry of compounds of noble gases, it becomes important to understand the answers to some important questions. First, what are the factors responsible for late discovery of compounds of noble gases? Second is, why do most of the compounds involve xenon, fluorine, and oxygen? So, late discovery of compounds of noble gases. Prior to 1962, it was believed that noble gases do not combine because they have stable electronic configurations. Many attempts were made to prepare their compounds, but all these attempts proved to be unsuccessful. Moisen in 1895 had reported that there was no chemical reactivity between fluorine and argon. This led Ramsay to conclude that noble gases are chemically inert. This conclusion was also supported by the concept of valency. According to this concept of valency, the electronic configuration having 8 electrons in its valence or outermost shell has been taken as the criteria of stability and inertness. That is why the noble gases were assigned zero valency and this group was designated as zero group. However, the concept of octet configuration of noble gases suffered setback because of discovery of compounds of like platinum fluoride, sulfur fluoride, and iodide fluoride, which had more than 8 electrons in their valence shell. This, however, did not make the scientists to make more serious attempts because the noble gas seemed to have neither any tendency to lose electrons because of high ionization energy nor any tendency to gain electrons because of low electron affinities. Some other factors, in addition to chemical inertness of noble gases, which led to late discovery of noble gas compounds, are: first is lack of availability of fluorine of good quality. Okay. Second is non-availability of fluorine resistant greases. Third is non-availability of inert material to handle fluorine gas. Fourth is non-availability of large quantities of noble gases. Then why do most of the compounds involve xenon, fluorine and oxygen? We know that the tendency of an atom to lose electron is given by its ionization energy. If we see carefully, the ionization energies of these elements are given in table 1. It is noticed that, leaving aside radon, which is unstable, only xenon and to some extent krypton has ionization energy comparable with some common elements like carbon, nitrogen, and oxygen. Xenon, therefore, has the maximum tendency to lose electrons and thus forms the higher ionization largest number of compounds. Krypton comes next. Neon, argon, and helium, which have much higher ionization energy, form hardly any compound. Further, since the activity of xenon and krypton is due to their tendency to lose their electrons, it suggests that the combining atom should have strong affinity for electrons. Example should be strongly electronegative. Now, in the tendency to accept electrons from other atoms, it is for this reason that xenon and krypton form compounds mostly with strong electron acceptors, viz. Fluorine and oxygen. The most of these compounds are fluorides, oxyfluorides, and oxides. Xenon combines directly with fluorine. Its combines with oxygen are obtained from its fluorides. Xenon chloride is known but it is not stable. Only one compound with nitrogen is known but it is highly unstable. That is compound of xenon. Xenon forms a large variety of compounds with fluorine and oxygen in different oxidation states. These are xenon fluorides, xenon oxides, and xenon oxyfluorides. Let us discuss the methods of preparation, their stereochemistry, and important properties of these compounds. Xenon 2 compounds. First is xenon difluoride, that is XeF2. Preparation. It can be prepared by the following methods. First step, xenon difluoride is best prepared by heating a mixture of xenon and fluorine in molecular ratio of 2:1 at 400 degrees Celsius in a sealed nickel tube. On cooling quickly, a colorless solid xenon fluoride is obtained. Excess of xenon is used to avoid the formation of any higher fluorides such as xenon tetrafluoride. Second is it can also be prepared by subjecting a mixture of xenon and fluorine in the molar ratio of 2:1 to electrical discharge. Like xenon plus fluorine on electrical discharge gives xenon difluoride. Third is it is also formed by photochemical combination of xenon and fluorine in the presence of mercury vapor. In the way, xenon plus fluorine in the presence of mercury vapor gives xenon difluoride. Fourth is it can also be prepared quantitatively by fluorination of xenon by oxygen monofluoride, that is O2F2, at minus 78 degrees Celsius. In the way, xenon plus oxygen monofluoride in the presence of minus 78 degrees Celsius gives xenon difluoride plus oxygen. Its properties: xenon difluoride is a colorless crystalline solid which melts at 129 degrees Celsius. It is the least volatile of xenon fluorides. It is stable in pure and dry state and can be stored in nickel containers. It dissolves in hydrogen fluoride without reacting with it. It reacts with hydrogen to give hydrogen fluoride and xenon. Like xenon difluoride plus hydrogen gives xenon plus 2 hydrogen fluoride. Next is it gives substitution reactions with strong protonic acids. Like xenon difluoride plus HX gives FXEX plus HF, where X is equal to ClO4 negative or CF3COO negative or CSO3F negative, etc. Next is it hydrolyzes slowly but completely in acidic and neutral or alkaline solutions. Like 2xCF2 plus 2H2O gives 2Xc plus 4HF plus O2. Next is it oxidizes iodine in the presence of BF3 to give IF, like XCF2 plus I2 in the presence of BF3 gives 2IF plus xenon. Next is it reacts with NO and NO2. XCF2 plus 2NO gives nitrosyl fluoride plus xenon. Next is it reacts with sulfur trioxide to give xenon. Like XCF2 plus 2SO3 gives xenon plus peroxidisulfuryl difluoride. Next is it is a mild fluorinating agent. Thus it reacts with benzene to give fluorobenzene. It also fluorinates ethylene to 1,1-difluoroethane. That is ethylene plus XAF2 gives 1,1-difluoroethane plus xenon. Next is it is also a strong oxidizing agent. It oxidizes HCl to Cl2, Ce3 to Ce4, Cr3 to Cr6, and BrO3 negative to BrO4 negative. Next is xenon difluoride is anhydrous hydrogen fluoride, reacts readily with platinum metal, sulfur powder, and iridium to produce highest fluorides. Next is in BrF2 solution, xenon difluoride acts as a Lewis base and forms adducts with composition XCF2 into MF5 and XCF2 into 2MF5 and 2XCF2 into MF5, where M is equal to phosphorus, arsenic, Sb, etc. These compounds XCF2.SbF5 and XCF2.AsF5 exist as ionic spaces respectively. Similarly, the XCF2 plus 2SbF5 gives XCF2.2SbF5. The compounds XCF2.2SbF5 has been shown to contain XCF positive and Sb2F11 negative ions. The XCF positive ion is strongly bonded to Sb2F11 negative by a fluoride bridge between xenon and Sb. The ion contains two octahedra linked by a shared fluorine as shown ahead. XCF2 also reacts with arsenic pentafluoride in a different stoichiometry. 2XCF2 plus arsenic pentafluoride gives 2XCF2.AsF5. The ion Xe2F3 positive has the expected linear geometry around xenon and an angular geometry around the xenon fluorine. Structure and shape of xenon fluoride. Spectroscopic analysis has shown that xenon fluoride molecule has linear geometry. This is explained on the basis of the valence bond theory as follows. Xenon at the ground state has the valence shell electronic configuration 5s2 5p6. One of the 5p electrons get unpaired and promoted to the 5d orbital, resulting in two unpaired electrons, one in 5p and one in 5d orbital, in the excited state of xenon. Five orbitals hybridize to give five sp3d hybrid orbitals, which adopt trigonal bipyramidal geometry. The two orbitals containing single electron overlap with two fluorine atoms, forming two xenon fluoride bonds. The xenon and two fluorine atoms lie in a straight line, while the other equatorial positions are occupied by three lone pairs of electrons. The molecule has thus a linear geometry. The lone pairs are present on equatorial positions of the triangle in a plane. Because of the symmetrical arrangement of three lone pairs, each at an angle of 120 degrees, the net repulsion on bond pairs is zero. Therefore, xenon fluoride molecule is linear. Next is xenon 4 compounds. Xenon tetrafluoride. Its preparation, it can be prepared by following methods. First is it is prepared in good yield by heating a mixture of xenon and fluorine in the molar ratio of 1 ratio 5 in a nucleus at 400 degrees Celsius under pressure of 5 to 6 atm. Second is it is also synthesized by passing an electrical discharge through a mixture of xenon and fluorine in the molar ratio of 1 ratio 2 at minus 78 degrees Celsius. The pressure is maintained between 2 to 15 mm of Hg. Its properties are the important properties of xenon tetrafluoride are it is a colorless crystalline solid. Its melting point is 117.1 degrees Celsius. It sublimes readily. It dissolves in iodine pentafluoride and hydrogen fluoride without reacting. It is oxidized by hydrogen to hydrogen fluoride at 30 degrees Celsius. It is a stronger fluorinating agent than xenon difluoride. It converts Hg to HgF2, Pt to PtF4, NO and NO2 to NOF, and NO2F, SF4 to SF6, etc. It reacts with boron trichloride to form boron trifluoride. It undergoes disproportionation in water, giving a highly explosive solid compound, XCO3. But if the reaction is controlled at minus 80 degrees Celsius, it forms xenon oxyfluoride. It combines with molten TAF5 to form straw-colored XCTAF6 whole twice. It forms an addition compound with antimony pentafluoride. That is, XCF3 positive has T-shaped structure, that is trigonal bipyramidal with two positions occupied by lone pairs structure. The electronic structure of XCF4 may be written as this. Spectroscopic methods have shown that xenon tetrafluoride has square planar structure. This can be explained on the basis of valence bond theory as described below. Xenon atom in the ground state has 5s to 5p6 outer shell electronic configuration. In the formation of xenon tetrafluoride molecule, two of the 5p electrons are promoted to 5d orbitals so that there are now four unpaired electrons, 2 in 5p and 2 in 5d. The six orbitals now form unpaired electrons. The six orbitals 1 5s, 3 5p and 2 5d get hybridized to form 6 sp3d2 hybrid orbitals. These 6 sp3d2 hybrid orbitals are doped octahedral geometry. Four of these containing single electron overlap with two p orbitals of fluorine to form four xenon fluoride bonds. The remaining two positions are occupied by lone pairs. The molecule has square planar shape. Next is xenon oxyfluoride, XeOF. Its preparation. It is prepared by slow and partial hydrolysis of xenon tetrafluoride at a low temperature, that is minus 80 degrees Celsius. It is not a very stable compound. Structure. Spectroscopic methods have shown that xenon oxyfluoride has T-shaped structure. This can be explained on the basis of valence bond theory as described below. A xenon atom in the ground state has 5s2 5p6 outer shell electronic configuration. To account for tetravalence of xenon, that is 3 sigma bonds and 1 pi bond, 2 of the 5 p electrons are promoted to the 5d orbitals in excited state. In this case, the 5 orbitals 1 5s, 3 5p, and 1 5d get hybridized to form 5 sp3d hybrid orbitals. One 5d orbital is left unhybridized for forming pi bonds. Three of the five hybrid orbitals, which are singly filled, form sigma bonds with two fluorine atoms and one oxygen atom. One 5d orbital, which is not involved in hybridization and is singly filled, is used in forming an additional bond, which is a pi bond with the oxygen atom. There is thus a double bond, one sigma bond and one pi bond between xenon and oxygen atoms. Since the xenon oxyfluoride molecule involves sp3d hybridization, its structure should be trigonal bipyramidal. But due to the presence of two lone pairs of electrons occupying two positions in the structure, there is distortion in the molecule. The compound therefore has a T-shaped structure. Next is xenon 6 compounds, that is xenon hexafluoride. Preparation. It is prepared by the following methods. First is it is prepared by heating xenon with excess of chlorine in the molar ratio of 1:20 in a nickel vessel at 250 to 300 degrees Celsius under pressure of 50 to 60 atm. Second is it can also be obtained by the oxygen of xenon tetrafluoride with O2F2 under pressure. That is, it is also prepared by passing electrical discharge through a mixture of xenon and fluorine in the ratio of 1:3 at a low temperature. Xenon hexafluoride can be separated from xenon difluoride and xenon tetrafluoride by passing through NaF, which absorbs xenon hexafluoride at 17 degrees Celsius, giving Na2HCF8. On warming Na2HCF8 to 120 degrees Celsius, pure xenon hexafluoride is evolved. Its properties. It is a solid crystalline substance. It melts at 49.5 degrees Celsius. It is most volatile of all the fluorides of xenon. Its vapor have a greenish yellow color. It dissolves in hydrogen fluoride, giving a solution which is a good conductor of electricity. This is attributed to the formation of ions. Xenon hexafluoride thus differs from xenon difluoride and xenon tetrafluoride as it dissolves in hydrogen fluoride without reacting. It is reduced to xenon by the action of hydrogen, ammonia, and hydrochloric acid. It undergoes slow hydrolysis with atmospheric moisture and forms xenon oxygen, which is highly explosive. Careful hydrolysis in nickel vessel give colorless stable liquid, xenon oxyfluoride. It is extremely reactive, therefore it cannot be stored in glass or quartz vessel because of the following reaction which finally give the dangerously explosive xenon trioxide. That is 2HCF6 plus SiO2 gives 2HCOF4 plus SiFO. Next, 2HCOF4 plus SiO2 gives 2HCO2F2 plus SiFO. Next, 2HCO2F2 plus SiO2 gives 2HCO3 plus SiFO. It, it reacts with fluoride ion acceptors to form adducts. That is XeF6 plus PtF5 gives XeF6.PtF5. Next is XeF6 plus SbF5 gives XeF6.SbF5. Next is XeF6 plus AsF5 gives XeF6.AsF5. XeF5 positive has square pyramidal symmetry as given below. Next is with fluoride ion donors, it forms XeF7 negative and XeF8 2 negative species. XeF6 2 negative ion has a square anti-prismatic structure and shape of XeF6 molecule. The ground state outer shell electronic configuration of xenon is 5s2 5p6. Three of the sp electrons are promoted to the 5d orbital so that there are no unpaired electrons. 3 in 5 p orbitals and 3 in 5d orbitals. In this case, 7 orbitals, 1 as 3p and 3d, hybridized to give 7 sp3d3 hybrid orbitals, which adopt pentagonal bipyramidal symmetry. 6 of these orbitals containing single electron each are used in bonding with 6 atoms of fluorine. Due to sp3d3 hybridization, the molecule should have pentagonal bipyramidal structure, but it is slightly distorted on account of the presence of a lone pair of electrons at one position. However, there has been controversy regarding its structure. It is preferably believed to have a distorted octahedral structure in which all the 6 positions are occupied by fluorine atoms and the lone pair is present at the center of one of the triangular faces. Alternatively, it has been suggested that the lone pair is present in the middle of an edge. Next is xenon oxytetrafluoride, XeOFO. Its preparation, it can be prepared by the following methods. First is xenon tetrafluoride is prepared by partial hydrolysis of xenon hexafluoride. Like XeF6 plus H2O gives XeOF4 plus 2HF. Second is it can be prepared by the action of XeF6 on silicon dioxide. That is 2XeF6 plus SiO2 under 50 degrees Celsius temperature gives XeOF4 plus SiF4. Soon as the yellow color of XeF disappears, the contents are immediately quenched with solid CO2. It is done to avoid the formation of XeO3 explosive as XeOF4 plus SiO2 gives XeO3 plus SiF4. Third is it is prepared in appreciable quantities by heating a mixture of xenon and fluorine in the molar ratio of 1:4 in the presence of a large excess of oxygen at about 230 degrees Celsius. It can be purified by vacuum distillation. Like xenon plus oxygen plus 4F2 gives 2XeOF4. Its properties. It is a colorless compound melting at minus 46 degrees Celsius. It is reduced by hydrogen to xenon. It reacts with water or silica to form another oxyfluoride, that is XeO2F2, in which xenon remains in the same oxidation state. Further reactions give explosive compound XeO3. It reacts with F negative ion acceptors to form XeOF3 positive cation. The XeOF3 positive cation has the following structure in which the lone pair, the oxygen atom and the fluorine atom, occupy the equatorial positions of a trigonal bipyramidal structure and two fluorine atoms occupy axial position. Next is xenon XeOF4 reacts with nitrosyl fluoride NOF to give a crystalline compound NO positive XeOF5 whole negative. Xenon OF5 negative ion has a pentagonal pyramidal structure with the oxygen atom in the optical position. In this case, xenon atom is slightly above the plane of 5 fluorine atoms. Structure and shape of XeOF4 molecule. Xenon atom in ground state has 5s2 5p6 outer shell electronic configuration. In order to account for hexavalence of xenon in XeO4, 5 sigma bond and 1 pi bond, 3 of the 5p electrons are promoted to 5d orbitals when excited. The 6 orbitals, one 5s, all the 3 5p, and 2 of the 5d orbitals get hybridized to form 6 sp3d2 hybrid orbitals which adopt octahedral geometry. One of the 3d electrons remain unhybridized for forming pi bond. 5 of the singly occupied hybrid orbitals form sigma bond with 4 fluorine atoms and 1 oxygen atom. The 5d orbital, which does not take part in hybridization, forms a pi bond with the oxygen atom. Thus, oxygen is combined to xenon by a double bond, one of which is a sigma bond and the other is a pi bond. It may be noted that one of the hybridized orbitals contains a lone pair of electrons. The molecule has a square pyramidal structure. Next is xenon dioxyfluoride, that is XeO2F2. Preparation. It is prepared by mixing XeO3 and XeOF4 at a low temperature close to minus 78 degrees Celsius. The compound is purified by fractional distillation. Second is it is also formed when XeOF4 is hydrolyzed or reacted with silica. That is 2XeOF4 plus SiO2 gives 2XeO2F2 plus SiF4. Its properties. It is a colorless solid. Its melting point is 30.8 degrees Celsius. It is easily hydrolyzed to give xenon trioxide. It is slowly decomposes to give xenon difluoride and oxygen. Therefore, thermodynamically it is unstable. It reacts with SbF5 in HF and gives a white solid of composition XeO2 F positive sp2 F11 negative. This compound is unstable at room temperature and slowly decomposes to give XeF positive sp2 F11 negative and oxygen. XeO2 F positive has tetrahedral structure in which one position is occupied by a lone pair. Structure and shape of XeO2F2. In this case, 3 of the 5p electrons are promoted to 5d orbitals when excited. The 5 orbitals, 1 5s, 3 5p, one of the 5d orbitals, get hybridized to form 5 sp3d hybrid orbitals. Thus adopt trigonal bipyramidal geometry. 2 of the 5d orbitals are left unhybridized for forming pi bonds. The 4 hybrid orbitals form sigma bond with 2 fluorine atoms and 2 oxygen atoms. The remaining 2 singly filled orbitals, which do not take part in hybridization, form pi bonds with the same 2 oxygen atoms. Each oxygen atom is thus bonded to xenon atom by a double bond. one of which is a sigma bond and the other is a pi bond. It may be noted that one of the hybrid orbitals contains a lone pair of electrons. The molecule does not have a regular symmetry. There is, however, a slight distortion due to the presence of a lone pair in one of the equatorial positions. Next compound is xenon trioxide, XeO3. Its preparation. Xenon trioxide is prepared by the hydrolysis of XeF6 or XeF4. 6XeF4 plus 12H2O gives 2XeO3 plus 4Xe plus 6HF plus 3O2. Or XeF6 plus 3H2O gives XeO3 plus 6HF. However, the last reaction proceeds through the following stages. XeF6 plus H2O gives XeOF4 plus 2HF. XeOF4 plus H2O gives XeO2F2 plus 2HF. And XeO2F2 plus H2O gives XeO3 plus 2HF. Great care should be taken during its preparation because it is highly explosive. Its properties. Xenon trioxide is a white non-volatile solid. It is soluble in water. It is quite stable in aqueous solution. However, it explodes violently when dry. It acts as a powerful oxidizing agent in acidic medium. For instance, it oxidizes Pu3 positive to Pu4 positive in the presence of H positive ions. The advantage of this reaction is that the only byproduct is xenon gas, which, being inert, does not introduce any extra complicating reaction. It also reacts with potassium iodide, giving 3 moles of iodine per mole of xenon trioxide. It undergoes disproportionation reaction when dissolved in sodium hydroxide and forms sodium perxenate, that is Na4 XeO6 into 8H2O. The X-ray analysis of sodium perxenate reveals the existence of the octahedral perxenate ion XeO6 4 negative in the substance. Sodium perxenate, when dissolved in acidic solution, decomposed slowly to give XeO3 and oxygen. Next is it reacts with XeF6 and XeOF4. Like XeO3 plus 2 XeF6 gives 3 XeOF4 and XeO3 plus 6 OF4 gives 2 XeO2F2. Structure and shape of XeO3 molecule. Xenon in the ground state has the outer shell electronic configuration as 5s2 5p6. In the formation of XeO3, 3 of the 5p electrons are promoted to 5d orbitals. The 4 orbitals 1 5s 3 5p hybridize to form 4 sp3 hybrid orbitals which adopt tetrahedral symmetry. 3 electrons on xenon remain unhybridized for forming sigma bonds. 3 of the 4 hybrid orbitals which are singly filled form 3 pi bonds with 3 oxygen atoms. 3 unhybridized 5d orbitals form 3 pi bonds with the same 3 oxygen atoms. Thus, each oxygen atom is bonded to xenon by a double bond. One of the hybrid orbitals contain a lone pair of electrons. Consequently, the molecule, instead of being tetrahedral, has a pyramidal structure as shown below. Next is xenon 8 compounds. Although there have been some reports of compounds of xenon in 8 oxidation states, yet these have not been confirmed by more recent works. The common compounds suggested are XeF8, XeO4, XeOF6, XeO3F2, and XeO2F4. Among these, XeO4 has been prepared successfully. XeO4 has been prepared by the action of concentrated H2SO4 on sodium or barium xenate Na2XeO6 or Ba2XeO6. It may be purified by vacuum sublimation at minus 78 degrees Celsius. It is unstable and decomposes to xenon and oxygen. It is very explosive and explodes even at minus 40 degrees Celsius. Like xenon tetroxide gives xenon plus 2 plus 643 kilojoule. It has tetrahedral structure. Compounds of other noble gases. Recent experiments have shown that krypton and radon can also combine with fluorine under suitable conditions, yielding krypton difluoride and krypton tetrafluoride and radon difluoride. Krypton difluoride preparation. It is prepared by irradiating a mixture of krypton and fluorine at very low temperature, that is minus 193 degrees Celsius. Irradiation can be carried out by X gamma rays, UV light, or by electric discharge. Krypton plus fluorine in the presence of gamma rays at minus 193 degrees Celsius gives KrF2. Its properties are KrF2 is a colorless solid. It is easily hydrolyzed. It is a powerful oxidizing and fluorinating agent. It forms adducts with SbF5 and AsF5. Structure. The structure of KrF2 is similar to that of xenon difluoride. It also involves sp3 hybridization of 5 orbitals. Two of these hybrid orbitals form sigma bonds with two fluorine atoms, and three positions are occupied by lone pairs. The geometry is linear. KrF4 and oxides have not been claimed definitely. Radon difluoride can also be prepared by similar methods, however, it is highly unstable. Are compounds of helium and neon possible? In normal state, all the s and p orbitals of xenon, krypton, and radon atoms are fully filled. However, there are vacant d orbitals in the valence shell which allow for the promotion of one or more electrons from d orbitals for the formation of unpaired electrons. If this be the case, it seems that helium and neon will never form compounds because they have no d orbitals at all. The promotion of electrons from s or d orbitals to next shell is highly unfavorable. Moreover, the ionization energies of helium and neon are considerably higher than those of xenon and krypton. This fact also rules out the possibility of the formation of compounds of helium and neon even with fluorine and oxygen.